Yay!
Yay! Hey, let's follow up a little bit on last time regarding how Newton probably knew that he was right, or at least good evidence that his universal law of gravitation was right. And what we're going to do is look at something that was known about in his own lifetime called Kepler's third law. Johannes Kepler, a brilliant mathematician in his own right, noticed patterns in the motion of the planets. One of the patterns that he noticed was this one. And it was where the square of the period of the planet was proportional to the distance away. Let's see, for distance we're using r, right? So it's proportional to the distance away from the sun cubed. It was just a mathematical pattern to Kepler. He didn't know why it was true. He just noticed that it was true. If he noticed that if you took the square of the periods of the planets, that equaled to, as it turned out, the cube of the distances of the planets away from the sun. So in that sense, it was universal, but there was no why, right? It was just the pattern. Kepler had no idea why it was true. There was no theory as to why it was true. But Newton, using his law of universal gravitation, showed that Kepler's third law, this relationship, was a consequence of his law. So let's see how it was done. Okay, so we go back to circular motion, right? For circular motion, you sum the forces on something, set it equal to mass times how it accelerates. And so for the case of like a planet or satellite going around a massive object, the only force acting, we'll say, is gravity. So you would just have g times the mass that you're orbiting times the mass of the satellite divided by distance squared is equal to AC, right? And so that's going to be equal to m times v squared over r. There we go. And generally, the force of gravity is in the same direction towards the center, right? The centripetal, that's the direction of the centripetal force. So they both have the same sign. Okay, well, the mass of the orbiting body, the satellite, that doesn't matter, it cancels out. And then we're going to use something that we used last time. Remember, I can say remember because it was in the last video. Remember that speed, another way I can write down speed is just distance over time. So if something is orbiting, what distance does it go in one orbit? It goes the circumference, 2 pi r. And what time does it take? It's the period, t, right? So I can just take that v, bloop, plug it right in there. And here's what I get. I get gm over r squared is, what would that be? 4 pi squared r squared, but there's an r in the denominator. Yeah, so there's an r up top, and then I got my t squared. There we go. And now what I'm going to do is just solve for t squared to make it look like Kepler's third law, right? So this is just going to be, if I solve for t squared, then I'm going to have t squared is 4 pi squared over gm r cubed. And look, that's it. Oops. A nice shaded box. There we go. That's it. That's Kepler's third law. So there's the t squared, and it's not just proportional to r cubed, but we have the proportionality constant, right? That's just a bunch of constants. 4 pi squared, the gravitational constant g, and then m, the mass of the thing you're orbiting, the central mass. That's the exact relationship. So Newton was able to show that Kepler's third law was just a consequence of his more universal gravitational law. Which again was a triumph of physics. So let's see how it works. The utility in this is that if we know the period of something, which often we can just watch, even a partial orbit of something like an asteroid going around the sun, we can sort of extrapolate around to the full orbit. And just by knowing how long it takes for something to go around the sun, now we instantly know how far away from the sun it is, because that's the way gravity works, which is it's a very neat thing, because most of the time asteroids or planets or whatever, in telescopes they just show up as dots. There's no real distance information. So extrapolating the orbit and finding out the period t, we can immediately calculate its distance, which is great. So Let's see. How about... Oh, let's just do a special example. Oh no, can I spell it right? Geosynchronous. Some satellites around the Earth are put into geosynchronous orbits, and all that means is that they stay over the same place on the Earth as the Earth spins. So another way of saying that is, if something is going to stay right over you as the Earth spins, that means its period has to be 24 hours, the same as you, right? Because then, if its period is 24 hours, then it'll stay relative to you. It'll stay in the same spot in the sky. So that's really useful. If you want to communicate with the satellite, you want to make sure it doesn't move, right? It stays in the same place. So satellites in geosynchronous orbit are a fixed distance away from the Earth. Let's figure out what that is. Geosynchronous means that T is 86,400 seconds, right? One day. So I can solve for R. So my R is GMT squared over 4 pi squared to the 1/3 power. So we already know what T is. The only mystery is M. That's the central mass thing. That's the Earth. So if you plug in ME, so if you plug in the Earth's mass, which we'll talk about in just a second, now you can calculate what that number is, and I've already done it, and that number turns out to be about 42 million meters, 42,000 kilometers. But remember, you have to be careful. Remember, that's the R. That R is always between the centers of the objects. So that's 42,000 kilometers from the center of the Earth. So minus the radius of the Earth is something like, it'll end up being something like 36,000 kilometers above the surface. Something like that. So what is that, like 20,000 miles from the surface of the Earth? So that's like a tenth of the way to the moon. I don't know, something like that. So that's how high a satellite has to be in order to have a period around the Earth of 24 hours. Very cool. Now what we can do. Often what happens is when you're watching rotating bodies, when you're watching things in space, you know the period. You just wait around and see how long the period is. So T is something that you would know. And often if you're watching the system, you know what R is. You can measure R, right? So this is a way that you can calculate the mass. The only other unknown there might be the mass of the object. So for example, let's calculate the mass of the Earth, just based on watching the moon, right? That's the obvious thing. So in Newton's time, or at least shortly thereafter, we could calculate the mass of the Earth, which is a fantastic thing because you can't, put the Earth on a scale or anything. So what's the mass of the Earth? Well, I can just solve for M. So the mass of the Earth is just going to be at GT squared. Oops. That's not even right. The mass of the Earth is just going to be 4 pi squared over T squared, GT squared, times R cubed. Okay, so let's just put the moon's data in there. We could do it for satellites too. But the moon is something that was easily observed, especially back in times before there were satellites. They could calculate the mass of the Earth, which is cool. So let's see what that would be. That would be 4 pi squared. The distance of the moon is 3.84 times 10 to the 8th cubit. And then I got my G. I'm not going to bother writing it down. It's just a constant. And then the T. How long does it take the moon to go around? I think we already calculated that, right? I think it was like 2.3 times 10 to the 6 seconds. It's like 27 days, 27 point something days. And then you square it. And when you calculate all this, you get something like 6 times 10 to the 24th kilograms. That's the mass of the Earth. So It was known, the mass of the Earth was known, I mean, actually like 400 years ago, which was kind of a cool thing. But all this comes out of Newton's gravitational law. In fact, we use this in astrophysics all the time. If you see two bodies orbiting each other, we can calculate the mass of the system. We know what the mass of Jupiter is. Why? Because we can see the moons going around Jupiter. So we just measure how far away they are from Jupiter. And then we measure the periods of the orbits, which is easy to see. It's easy to watch. So getting the masses of astronomical objects is simple if you can see other objects orbiting them. So such is the power. Oh, we can even get the mass of the galaxy, right? By knowing how long it takes objects to spin around by looking at their orbital speeds around the centers of the galaxies, we can calculate the mass of galaxies, which turn out to be, hundreds of billions of solar masses. So such is the power of Newton's universal gravitational law.